Hey guys, in the last two lecture we have seen sleeve coupling and clamp coupling. So in today's lecture we will see flange coupling. So a flange coupling usually applies to a coupling having two separate cast iron flanges. So as we know that in clamp coupling the parts where there were two parts uh, cut in half. Here also there are two parts but in a different way. So each flange is mounted on the shaft end and keyed to it. The faces are turned up right angle to the axis of the shaft. So let me draw so it will be more clearer. So suppose this is the shaft. Suppose this is a shaft having diameter of d, small d, and here there is a hub. So here there is a hub, and above hub there is a flange. So this is hub and this is flange. So here you can see this is a cross section area, and here there is a bolt. So here this is the bolt, and here there is a key. So this is the key. Now the diameter of the hub will be capital D, which will be equal to 2 times the diameter of the shaft, and the diameter of the flange, this D, will be 4 times the diameter of the shaft, that will be equal to 4D, and this will be equal to 2D, and the distance between the bolt will be equal to 3D. This will be equal to 3D. So D, 2D, 3D, 4D. So this is the unprotected type flange coupling. Similarly, the same will be here on the other side. So this helps to bring the shafts into the line and to maintain the alignment. So the two flanges are coupled. So here these two flanges are coupled together by means of bolts and nuts. So as you can see, this is one flange and this is another flange. These are coupled with the help of bolts and nuts. So so the flange coupling is adapted to heavy loads, and hence it is used on a large shafting, and the flange coupling are one of the three types. So there are three types of flange coupling. So what are they? So I will list it down. So number one is unprotected type flange coupling. Then second is protected type. Second is protected type flange coupling, and third is marine type. And third is marine type flange coupling. So uh, so now what is the difference between this protected type and unprotected type and protected type? So in unprotected type, as you can see that here the bolts are protected and it is open to the atmosphere, So here the balls can be uh, hit by can be hit by a workman or something, while in protected type the flange is included inside the bolt, so it is protected type. So there's the main difference. And here in marine type flange coupling, the flanges, so this flanges are here are forged as integral part of the shaft. So this will be forged inside this of the shaft. So the flanges are held together by means of tapered headless bolts numbering 4 to 5 depending upon the diameter of the shaft. So here that is inside the shaft. So that are the three main type. Now we will see the design of flange coupling. So which are the various parameters which we need to consider for designing the flange coupling. So we will just give first nomenclature. So small d will be the diameter of the shaft. Then capital D will be outer diameter of the hub. Then small d1 will be equal to nominal or outside diameter of the bolt. Then capital D1 will be equal to diameter of the bolt circle. Then N is equal to number of bolts. N is equal to number of bolts. Then T1 is equal to thickness of flange. Flange thickness. So not T1, we will call it as TF. So it's flange thickness. Then various shear stresses and uh, allowable crushing stresses. So there are three shear stresses, that is TS, TB and TK. TS, TB and TK. So these are the shear stresses for the shaft. S for the shaft, B for the bolt, and K for the key. So there's three shear stresses and crushing stresses. There will be sigma B and sigma CK. So the crushing stresses for the bolt and for the key. So this is the nomenclature. Now we will design. So we will design for the hub. Also we will design for the key, and we will design for the flange and for the bolts. So each and every component we will design. So let's start with first the design of the hub design. So the hub design, by considering it as a hollow shaft, so it is transmitting this same torque T will be equal to pi by 16 tau d cube. So uh, tau into, as it is a hollow shaft, so it will be equal to d raised to 4 minus d raised to 4 upon d. Now d, capital D, is diameter of the hub and diameter of the shaft or inner diameter of the hub. So this is the formula for the design for the hub. So the outer diameter of the hub is usually taken as twice the diameter of the shaft. So generally we take capital D as 2D, 2 small d. Therefore, from this relation, the induced shearing stress in the hub may be checked, and the length of the hub L is taken as 1.5 d, and generally we take d is equal to 2 times d. Okay, so second is design for the key. So key design. The key is designed with usual proportions and then checked for shearing and crushing stresses. So we'll check for shearing and crushing stresses. So the material for the key is usually same as the shaft, and the length of the key is taken as equal to the length of the hub. So length of key is equal to length of hub. So the length of hub is 1.5d. Then third, we'll see it is designed for flange. So the flange at the junction of the hub is under shear while transmitting the torque. Therefore, the torque transmitted T will be equal to circumference of the hub, that is pi into d, into thickness of the flange, that is Tf, into shear stress of the flange, that is equal to tau, and into radius of the hub, so which will be equal to d by 2. So T will be equal to pi d square by 2 tau c Tf. So torque T is pi d square by 2 tau c Tf. The thickness of flange is usually taken as half of the diameter of the shaft, that is d by 2. Therefore, from this relation, the induced shearing stress in the flange may be checked. So this tau can be checked. Now fourth is designed for bolts. So bolts are subjected to shear stress due to torque transmitted. So the number of bolts n depends upon diameter of the shaft and the pitch diameter of the bolts. D1, that is taken as 3D. So we know that load on each bolt is equal to pi by 4 d1 square tau b. So which is equal to, so total load on all the bolts, so total load will be equal to pi by 4 d1 square tau b into n. So the torque transmitted T is equal to force load, that is force into radius. So pi by 4 d1 square tau b n into d1 by 2. So from this equation, the diameter of the bolt d1 may be obtained. Now the diameter of the bolt may be checked in crushing. So we know that area resisting the crushing of all bolts is equal to n into d1 into tf. So this is the area. So the crushing strength of all the bolts will be equal to area into sigma cb. So this is the force. So torque, it will be equal to force into radius. So it will be equal to n into d1 into tf into sigma cb into d1 by 2. So this is the torque based on crushing stress, and this is the torque based on shear stress. So this is the whole design process. This is the design of a flange coupling. Now let's see an example, so that it will be more clearer. So an example is given. Suppose design a cast iron protective type flange coupling. So what is the material? Cast iron, and protective type flange coupling. Coupling is flange. Coupling to transmit the power of 15 kilowatt. So power is given as 15 kilowatt at 900 rpm. So n is equal to 900 rpm. From an electric motor to a compressor. So from an electric motor to compressor, so the service factor may be assumed as 1.35. So service factor K is equal to 1.35. So the following permissible stress may be used. So stresses are given, that is shear stress for the shaft, bolt and key material. So tau S is equal to tau B is equal to tau K is equal to 40 MPa. Then crushing stress for the bolt and key, sigma CB is equal to sigma CK is equal to 80 MPa. And shear stress for cast iron, so TC is equal to 8 MPa. So the protective type flange coupling we have to design. So we will design for first hub design. So for design for hub, we know that the maximum torque T max is equal to pi by 16 tau c into d raised to 4 minus d raised to 4 upon d. So this is the formula. Now what is the torque transmitted by the shaft first? So torque transmitted is P into 60 divided by 2 pi n. So this will come equal to 159.13 Newton meter. Since the service factor is 1.35, the maximum torque transmitted T max will be equal to this torque T into 1.35. So which will be equal to 215 into 10 raised to 3 Newton mm. So this T max we have found. Now we know that torque transmitted by the shaft T will be equal to, so T max will be equal to pi by 16 tau s dq. So with this help we can find the diameter. So T max we have 215 into 10 raised to 3, and tau s shear stress. Shear stress was given. Shear stress is 40 MPa. So shear stress is 40 MPa. So diameter D we can find, that is 35 mm, and we know that diameter of the hub will be equal to 2D, so this will be equal to 70 mm, and length will be equal to 1.5D, which is equal to 52.5 mm. So we have found all the parameters of the hub, but then also we need to check it for shear stress again. So we will put these values in this equation. T max, the T max we have, D we have, and small d and capital D we have. So with this help we can find tau c. So tau c we will get is equal to 3.4 MPa, so which is less than the permissible, that is 8 MPa. So it is a safe design. Similarly we have to design for the key, second key. So key, since the crushing stress for the key material is twice the shear stress, that is sigma ck equal twice tau k, therefore square key may be used, and from that we can find the shaft diameter, shaft of 35 mm diameter, for we have width is equal to 12 mm, thickness will be equal to 12 mm, and length will be equal to 52.5 mm. So let us now check the induced shear stress by considering T max formula, shear stress and crushing stress. So T max is equal to LW tau K D by 2. So L we have, W we have. So this is L, this is W. T max we have, and D diameter we have. So you are left with tau k. So tau k will be equal to 19.5 MPa. So which is, permissible. Then similarly sigma k. So T is equal to L into T by 2 into sigma Ck into D by 2. So sigma Ck will be 39 MPa. So sigma C is also under permissible, that is 80 MPa. Then we have to design for the flange. Third, we have to design for the flange. So flange is equal to Tf is equal to 0.5 into D. So the thickness of the flange is 17.5 mm. And fourth, if we have to check this for the shear stress also. So shear stress will be come out tau c is equal to pi d square upon 2 tau c tf. So which will be equal to tau c will come 1.6 MPa. So T max is equal to. So similarly design for the bolts. So for bolts, so D1 is the suppose nominal diameter of the bolts. So the diameter of the shaft is 35 mm. Therefore number of bolts is equal to 3. D1 is equal to 3D is equal to 105 mm. So T max is equal to pi by 4 D1 square TB and D1 by 2. So from this equation we will get D1 is equal to 6.6 mm. So assuming coarse threads, the nearest standard size of the bolt is M8. Other proportions of the flange will be D2 is equal to 4D and TP is equal to 0.25D, which is equal to 8.75 mm. So which will take us 10 mm as a round off. So all the four are designed. So I hope you understood this, and see you in the next lecture. Thank you very much.